Hello, welcome to ICAPMOT. We are very pleased to have you here today, Dr. Amarjeet Kaur. So today we have our senior professor from Department of Physics and Astrophysics at University of Delhi in Experimental Condensed Matter Physics. Through her academic leadership and research contribution, Professor has supported the development of many functional materials and device-oriented technologies, including the development of supercapacitor electrodes from mustard seed biowaste, which seems very innovative. With a very distinguished academic career and a strong research leadership, she has made several contributions to functional materials, device oriented technologies, and innovation in energy, sensing, and smart material applications. We are very honored to have her here today. She has made a widely recognized in both academic and dedicated mentor to aspiring physics across India. Welcome, Dr. Amrish Kaur. We are eagerly waiting for your presentation today.
Yeah, thank you, Madam Chairperson, for such nice words for me. Thank you so much. And I'm thankful to Dr. Conrad for giving me the opportunity to present my work once again over here. And so I'm going to share my slides now. Just please let me know that are they visible?
Sorry, please say that again, please.
Yeah.
Yeah, we are able to. We are able to see your screen.
Yeah, thank you so much. So today I'm going to present my work on zinc-ion batteries. So which are the future of sustainable energy storage and release. All of us know that our life begins with the use of lithium-ion batteries in the morning, and the lithium-ion battery is a part of our daily life. We are using it in mobile, in laptops, and everywhere. But on the other side, we cannot forget that because lithium is a rare metal and it is not easily available. So there are people are working in the scientific community on other options like zinc, magnesium, etc., calcium, etc., aluminum ion batteries, etc., because we need something a very eco-friendly solution. So because it is very difficult to dispose lithium. So this is hazardous also. Its energy density is very high. The number of accidents with lithium-ion batteries are also increasing. So there's a lot of search going on to replace lithium with alternative solutions. So we are working in the area of zinc-ion batteries. So this is what I'm going to present it today. And I am from Department of Physics, Delhi University. Professor Conrad being there. So our campus actually, the college, the university is spread all over Delhi, but our campus, that is the science faculty, is here somewhere in the north campus in Delhi University. So, so this is the science block. We have the rugby stadium also. We have computer centers. This classroom. This is this is a very heritage building. That is the old Vice Regal lawn, and then we have different science departments. So giving some glimpse about our university. So now my lecture plan is that I'm going to start with the basic introduction about the zinc-ion batteries, their construction, then their charge storage mechanism, then zinc characterization of cathode material and device characterization. So as I was telling you that why the zinc ion batteries are gaining global attention because as you know that the global energy storage mechanism, it's a multi-billion economy and it is growing very fast, right? Right now we are somewhere here around 243 US dollar billion dollar economy, but gradually it is expanding, and by 2034 it will reach around 740 US dollar billion US dollar. So then coming to the why there is a need and of oil to replace lithium is that because one thing is that it is a costly process. That way, zinc is quite cheaper than lithium. It is hardly $2 per kg, whereas lithium is $19 per kg. Of course, this is non-inflammable. It is easy to handle it. Zinc is non-toxic and environment friendly, and and you don't need specially moisture-free, humidity-free conditions like glove box and all. And it has stable electrochemistry and a good redox potential and with the high capacity also. So now, if we look at the construction of any battery, we have a cathode, that is the positive electrode, the anode, which is the negative, and then there is an electrolyte, which provides the medium for the flow of ions. Because this is all thing depends upon the flow of ions. And then there is a porous electrically insulating film that physically separates the two electrodes. And the current collectors are the bridging components between the electrodes and the external circuit. So this is the basic uh, construction of any battery. So in the case coming to the zinc ion battery, so one of the electrode, that is anode, is zinc, of course. Then you have to judiciously choose the current collector, because it all depends upon the how good is your current collector, in the sense that it is the Faradic process. Faradic process, it means that the electrodes themselves take part in the electrode reactions, and the transfer of electrons is between the electrode and the electrolytic species. And the zinc ions, when we apply some, when the reaction takes place, the zinc gets oxidized to zinc ions, and these zinc ions are intercalated and deintercalated into this cathode. So this cathode material is very important in the sense that how much ions it can intercalate and how fast they can be intercalated and disintercalated. Because while charging this battery, you have to it has to intercalate, and then while discharging the battery, it will the charge will flow in the opposite direction, right, to supply the voltage. So generally, the materials which are explored for the electro current collectors, like are like the most popular one is the manganese based materials, because you will find number of publications in this case. And of course, manganese based materials have good cyclability. Cyclability means that how much quickly it can charge and discharge, and how much cycles it can sustain. Then the operating voltage also is good in this case. Then the other mostly this thing studied material is vanadium based materials, right? Here also you have a good cyclability, and the current the operating voltage is also better in this case, and energy density and specific capacity is also very good. Energy density means that how much energy you can store per kg of this of the material, and specific capacity is the capacitance per unit gram which it can release. The other materials like polymer based materials and then organic based materials are also, people are exploring them because of the flexibility, right, and the lightweight. And so the good cathode materials are the one, when you design a battery, it should give you a good specific capacity, the energy density, the operating voltage should be very good, the rate capability should be good, the cyclic stability also should be good. So that is how much time, how much, because on cyclic stability, the life of the battery depends, that how much quickly it can charge, discharge, and for how many cycles it remains stable, right? So the structure and the composition of the cathode determine the charge storage mechanism, and of course it dictates the overall safety of the device. Now, vanadium based cathodes, right? Why they are popular? Because vanadium, it can exist in multiple oxidation states. There's a large interlayer spacing between them. There's a good ion intercalation, then open, and there is the diffusion channels are very good to allow the ions to flow through, and then it gets tunable also. But on the other hand, there are challenges also, that it has a low operating voltage. It dissolves in the aqueous electrolyte. There is a poor electronic conductivity, because for a good battery you need both a good ionic conductivity and good electronic conductivity. Then you have the charge storage mechanism is not very easy to understand because of the multiple oxidation states. And then there is a structural distortion also. So a lot of work is going on among these scientific communities to improve the vanadium to develop the strategies to improve the vanadium-based cathodes, like nanostructuring of the electrodes. That then you have to optimize the electrolyte. Then you have to see the doping is there. What kind of doping should be there? It should be defect-free and all those things. And there's the other important thing, that is a composite formation, that lets form a composite so that we can have whatever the properties which are absent in vanadium, that can be taken care by the composites. And that is what we have, this research is based on that, which we are keeping in mind. So, so what we have done is we have prepared we have incorporated the graphene nanoribbons in the cathodes. Why? Because graphene, as I told you, that vanadium itself, vanadium compound, they don't have very good electronic conductivity, but graphene ribbons have very good electrical conductivity, especially at the edges. So we have high electronic conductivity, we have increased surface area, we have a good tunable electronic structure, and which enables fast charge transport, and it offers low internal resistance. So we started, we have, for this, we have used the ZIF-67, that is the metal oxide framework. Metal oxide frameworks are always better to use because they are porous structured crystals, and they compose of metal clusters linked with the organic ligands. They possess the characteristics of control for pore size, and readily available metal sites make them desirable for various applications. So we have used this ZI-F67 MOF as a precursor to synthesize cobalt vanadium oxide. So in this we have vanadium oxide cage in which cobalt is entrapped, and then we have graphene nanoribbons. They are prepared by the oxidative unzipping of the multi-walled carbon nanotubes, and then we have combined CVO and GNR hydrothermally to form the porous CVO GNR composite. So they are stirred, then we have hydrothermal autoclave, then we have annealing, then we have after annealing for 400 at 400 degrees Celsius, then we have the CVO GNR, which is to be treated hydrothermally, and then we have to wash it multiple times to get the CVO GNR composite. So these are the HR10 images of our synthesized material. So you can see from these from this that they are the CVO. The first is the cobalt vanadium oxide material, which you can see that this is spherical. The particles are spherical in nature. Then we have graphene nanoribbons. Right? One can see that there are sheets of graphene nanoribbons which are wrapped around each other, and then the d spacing in the case of CVO is around 1.47 angstrom, and this is there are two kinds of planes which are there. Cobalt CO3 V2O8 is also present here, and then we have this CVO GNR. So in this one can easily see that within these ribbons, there the cobalt nanoparticles are the CVO nanoparticles are entrapped. So looking at the XRD, the graphene nanoribbons have typical peak at around 2 theta at around 8.2 degree, which is a characteristic peak of the GNRs, and then the peak at 26.8 degree down here. Okay. So this is the typical 002 plane, which is observed in the XRD spectra of both CVO as well as GNR. So this is present in the this peak is present in the composite also, CVO GNR, and so so whatever the characteristics are of CVO and what the characteristics of GNR, both are present in the CVO GNR composite. So and then we have the so basically the XRD characterization of the synthesized sample confirms that the presence of V2O5, that is around 33.7%, and there is a cobalt V3O8 which is 59.23%. So both the phases are present in the CBO sample. So their relative phase contributions were determined through, then we did the poly refinement and all those things to find out this particular contribution. Then we have this FTIR also confirmed the synthesis of our material. We use both Raman spectroscopy as well as the Fourier transform infrared spectroscopy. The Raman spectrum exhibits the peak at around 306.09, whereas the OVO bending is there. And if we look at the FTIR spectroscopy, then the OVO bending peak is there around 800. Here it is there. This is the characteristic peak which is present in the case of the composite. And also there are the peaks in the CBO GNR composite. There are the peaks here. These are the signature peaks of around 146.6 nanometer and a centimeter inverse. And then we have the other characteristic peaks which are present in the which are present here in the CBO GNR, which confirms that it contains the signature of both GNR as well as CBO. So then this is our device, that is the battery device is there, that cathode is the CBO GNR. Then we have the electrolyte, which is the zinc triplet, and it is mixed with the ethylene and the propylene carbonate, and then the other electrode is zinc. So in between we have to keep the spacers to avoid the shorting of the device. So because to get the uniform pores for the intercalation of the zinc and the intercalation, so we need a uniform porous structure. So BET analysis really helped us to see that whether this is our material is suitable to make it a cathode or not. So we can conclude that CVO depicts typically, if you look at the CVO, this is a typical type 3 adsorption-desorption isotherm indicating the weak surface interaction. And in contrast, you see that CVO GNR, it shows a little bit hysteresis also. It displays a combination of type 3 and type 4 isotherms, suggesting that adding GNRs in the introduces the mesoporosity while still allowing the multi-layer adsorption. So, the introduction of GNR enhances the, you can see that then we have this pore size distribution curve. So we can see that by addition of GNR, the BET surface areas of the pore has increased by an order. Then the cumulative pore volume also increases, and the mean pore diameter also reduces. So these are the very good characteristics for CVO GNR composite, which will be rather more suitable as compared to pure cobalt vanadium oxide. So now looking at the electrochemical analysis of these materials, so one can see that we have used the non-aqueous electrolyte, that because it has been observed from the previous study that most of the vanadium-based materials tend to dissolve in the diluted aqueous electrolyte. So that is why we have used the non-aqueous electrolyte. And the CV curve scan, because we have done this cyclic voltammetry at different scan weights. So we even from at the scan rate of 0.1 millivolt per second, it shows the multiple intercalation and deintercalation of zinc ions in the structure that can be explained with the two pairs of redox peaks. So there are two redox peaks. One is observed at the 0.851 voltage and the other is observed at 1.36 volts. And the reduction peaks are observed at 0.8 and 0.396 volts, which represent the two-stage redox transition from V5 to V4 plus and then V4 to V3 plus. And recent studies have revealed that the two redox peaks in CV can be attributed to the sequential interfiltration of zinc ions in the two distinct crystallographic sites. Now, these and one can also see that the CV curve of the CVO GNR cathode at the scan rate at different scan rates, that they retain their fundamental shapes despite subtle shifts in the peaks positions. So, what we can infer from here that because generally, if we plot the peak position, the peak current versus the scan rate, then we get the slope. Like it's a straight line that could that is by AB to the power B, and the value of this slope is 0.53 and 0.77. So when the B values range between 0.5 to 1, it represents a hybrid storage mechanism. That is, it has both the diffusion current is also there. So 0.53 corresponds to diffusion limited process, whereas the typical ion intercalation is there, and then 0.77 denote a dominant pseudo-capacitive response. So further, so we have the hybrid charge storage mechanism with diffusion and the pseudo-capacitive contribution, and then if we take the EIS spectroscopy, that is the impedance spectroscopy, in this case electrochemical impedance spectroscopy, we have used this bottle, that is two resistance with the CPE. Then in this case, the charge transfer resistance has a smaller value. So because smaller is the value, better the ion transport will take place. And so in this way, the CVO GNR is much better. So now, if we did this galvanostatic charge discharge also, and the uh, which shows that and we calculated the discharge capacity. The discharge capacity of the device is 466 milliampere per gram at 0.1 ampere per gram. It's a very good value, and the only thing is that now when it has to maintain its value up to 78 as much as it can possible, but this discharge capacity is 180 milliampere per gram even at the high current density of 2 ampere per gram. And energy density is also very good, so these are the values which are comparable. But only problem is that on which we are working right now is because it retained only 73% of the capacity after 1,000 cycles. So one has to really improve this value. That is, it should retain the almost same value if after the 1 lakh cycles or 10,000 cycles and so on. It is maintaining good value at the lower current rate, that is around 0.1, 0.2 ampere per gram. But as the current density is increasing, then these values tend to fall. So one need the specific capacity has to remain constant. The better is the device. So up to 1,000 cycle this is better, but beyond that the Coulombing efficiency also falls down. So so we are working on this. We have to improve the device further. But our zinc-ion battery by introducing the graphene nanoribbon is giving us a promising values, and so we have to further improve it to make it a product worth for industry. So with this, I would like to conclude my talk. So different facilities are there in my lab. So Professor Rizal has once visited our lab. So this is and then now I would like to conclude my talk. So we have developed a novel cathode material, cobalt vanadium oxide graphene nanoribbon composite derived from ZIF 67, a metal organic framework, and the graphene oxide nanoribbons. And this CVO GNR composite exhibits enhanced electrochemical properties due to the synergistic effect of vanadium-based compounds and graphene nanoribbons, which improve the material's electrical conductivity, surface area, and it provides faster and easier ion diffusion in the fabricated cell. The discharge capacity is also good at 0.1 ampere gram, but we have to work. We are still working on it to retain, though it is retaining a very good high capacity at 2 ampere per gram, but still the value we are working on to improve this value. And the cyclic stability test provides the 73% of the capacity retention after 1000 cycles at the rate of 2 ampere per gram, which demonstrate outstanding stability and the promising specific capacity. So with this, I would acknowledge all my research scholars and the fundings which I have got, and thank you so much for listening to me, and thank you once again, Dr. Rizal, for giving me the opportunity to present my work at this prestigious ICAPMOT 2026. Thank you once again.
Thank you so much for your presentation, for sharing your project with us. It was very insightful. And we just have a few questions in the chat for you.
Yeah, sure. Let me come back. Yes, tell me.
How can artificial intelligence and machine learning be used to optimize zinc-ion battery material discovery and performance prediction?
Oh, this is a very, very good question because there are thousands of combinations of the electrolytes and the electrodes, right? So choosing the appropriate, this AI is really helping us to, choose the appropriate material. In fact, this work is also one of my interns, he used the machine learning things and he gave us some options for of different combinations, because I gave him some parameters like, what should be the ion transport, what is the ionic conductivity, what should be electronic conductivity. And as a result of that only, he has given us some permutation combination and we have used this material. And especially for battery research for this thing, because there are multiple things involved, the kind of electrolytes, its viscosity, right? How the ion transport is there, then whether they are compatible with the electrodes. So there are thousands of permutation combination is there, and you cannot try all of them. So there, where this AI really helps us.
Thank you. What future breakthroughs could allow zinc-ion batteries to surpass lithium-ion batteries in energy density and commercial performance?
One thing is energy density and other is the stability, because stability is a big issue, that if you want to use something, because of course you can use them as a throwaway battery, like the flexible small batteries, and you can use it for some time. But if you really want to use it, like for example in your laptops, or where the batteries, they stay for a very long time and all, then you really have to improve. And again, it will depend upon the, everything lies that the synergy between the electrodes and the electrolyte. That is
Would
where
you
we have
say
to
it's
work
like a
upon.
sustainable solution
It will
instead?
definitely a sustainable system, because one thing, zinc is easily available, and zinc is not the toxic material.
Uh-huh.
And secondly, economically also, because for lithium, the reserves are very small, so you have to depend on some countries for that thing. So economically also, it is not very good option, because there is always an economical dependence on the other country. And third thing is that, because if you dispose it off, so zinc is not hazardous like lithium. So for lithium, you really need good measures to dispose of the thing or recycle it. For zinc, it is easy to recycle.
Okay.
So,
Thank you
so
for
the
sharing.
carbon footprint, yeah. So the carbon footprint in this case for the recycling is really zero for the case of zinc.
Mhm. Well, that's very like new information for us.
Yeah.
And I really hope like your research still breaks through and like you achieve what you're intending to achieve. Thank you for your presentation.